Okay, and today we are now to our final session on cryptography. So if you are tuning in for the first time, if you are looking at the CC exam or the Security Plus exam, this would be the session to help you on. Okay, I'm Benjamin, and before I get started, let's introduce to you this new quiz platform, which is totally free. Okay, and I'm really excited to announce our new quiz platform. We have our ISC2 CC and CompTIA Security Plus quiz on it. So there's a total of 132 questions in the pool already. I've actually vetted through every single question, so be assured that the answers are all correct and the explanations are all good. I'll be adding more questions to it as time passes. So we'll be the questions will be randomized, and you'll be taking up to 100 questions per session. Although you can end the quiz and stop it at any time. So let's quickly step through some. So which AAA component determines which action users are to perform? And authorization is the answer. Next question. Implementing a firewall reduce this is risk mitigation, and do you have explanations out here as well? And in the event that you actually answer incorrectly, actually they will flag out the correct answer, and there will be explanations as well. And if you have done 20-50 questions and you are tired and you don't have any time anymore, you can actually end quiz, and they actually give you a performance by your category, how many answers you got correct for each category, and you can review your wrong answers here again. So this is completely free. I'll leave the link to this site in the description down below, and I hope that you enjoy it. Thank you. Okay, so when we look at cryptography, there are a few concepts you want to look at. So on the exam itself, you may see encryption, which the aim of encryption is always confidentiality. So this is something always keep in mind. You may see something called hashing as well, and the aim of hashing is always on integrity, to provide integrity. And some of the concepts related to hashing, we have digital signatures, and we have something called salts as well, which we will cover later. Yeah. And finally, we look at public key infrastructure. Because the internet is huge, you cannot possibly trust every single person on the internet or know every single person on the internet. So how do you know who to trust? So we have this thing called public key infrastructure, which helps us to make that determination. Okay, so let's quickly take a look at encryption first. So one of the ways of encryption is called symmetric encryption. So when we look at symmetric encryption, it is fast compared to asymmetric. Asymmetric is always slow. Okay, and symmetric encryption, we only have one single key, and the same key is used to encrypt and decrypt. For asymmetric, we have something known as a public key and a private key. So there are two different keys. One can be used to encrypt and one can be used to decrypt. Okay, and the other things also you might have to kind of memorize, or which are the encryption algorithms which fall into this. So for symmetric itself, one of the predecessors we have is DES, and then the more recent one would have is AES. So these are the symmetric encryption algorithms. No way around it, you just have to remember which is which. So for asymmetric itself, there is RSA, and then the more recent ones is elliptic curve ECC. So when you see these acronyms, you know what it means. So another thing that may confuse you is that ECC is also used to refer to RAM, but this is different. So when ECC is used to refer to RAM, it's error correcting, and it's totally different from this ECC, which is elliptic curve cryptography. Yeah. So you may come across this. Just don't get confused. Yeah. Okay, and finally we look at something known as encoding. So sometimes there may be questions on encoding as well. And encoding is different from encryption in the sense that encoding, there is no key at all. So anyone who knows which encoding algorithm you use can actually reverse it without a key. Okay, and so some of the common encoding algorithms are something like base 64. So why do we do encoding? It's to actually change the format of the data itself. So it could be an image, and we want to send it over, let's say, a medium that only allows text, And how do we do it? So we do an encoding, and then someone else on the other end can decode again, and this would give you back to the image itself. So there is no key in encoding. This is the key principle here. Okay, with encryption done, let's look at hashing. So the difference between hashing and encryption is hashing is one way. Okay, when we hash, we cannot unhash. The only way to figure out what's the pre-image, what caused that hash, is to really brute force, try every single pre-image to see what caused it. So that's the idea of hashing. And hashing provides integrity. Hashing is also used, a lot of cases for password storage. So password storage, why do we use hashing? So imagine, you have this huge table here, and you have, let's say, user 1, user 2, and you have all their passwords here. Let's say if this table is actually leaked out, someone will be able to recover all their plain text password, which is not advisable, which is will be a bad thing. Yeah. So what we do is we hash it. So we hash it before we store, and when we hash, it's some gibberish that ends up here. And so what happens when user 1 tries to log in is when he supplies his password, we immediately hash the password, and then we compare the hash to this here. Does it match? If it match, then user 1 has supplied the correct password, and then we'll allow user 1 to access. So this is not stored anywhere at all, and then we'll actually just forget the plain text password. So this is a much more secure way of doing hashing, of storing passwords. Okay, since we are on the topic of hashing and securing passwords, let's look at this idea of something called salts. So the whole reason is a lot of people would actually use the same passwords, p@ssw0rd, a very common password, and every time you hash a password, you would end up with the same hash, and so people can actually come up with tables of commonly used passwords and what are the hashes, and crack it. So what hashing does is it appends a certain hash in front of every single password that is very different, and what would happen is that suddenly this password is not commonly used anymore. So what will happen is that we would append this in front of the of the password before we do the hash, and we compare it. So this thing here will never ever match whatever has been leaked out, whatever has been pre-calculated by all the threat actors. Yeah. So that's the idea of having a salt. And finally, digital signature itself. So digital signature actually uses asymmetric encryption. And so what happens is that let's say you have a document here, and then you want to sign the document. You use your private key to sign, and then you get a digital signature out of it. You'd send both the document and the digital signature over to someone else, and someone else can download your public key from the PKI, from the certificate authority. We'll talk about this later. He'll download it, he'll use the public key to actually decrypt the signature, and then you get back the hash, and then you see that does this match. If this match, it confirms that you sent out that and that's the idea of a digital signature. Okay, on to PKI. So the idea of a PKI is, let me find some space over here. Okay, so let's say there's a lot of people that want to talk to each other, but they have no idea whether each other can be trusted. So what they do is they upload their public key onto the PKI. So the public key is also very commonly called certificate. So actually the PKI would help to generate and certify the identity of each person here. And so everybody don't need to trust 1,000 of other people. They just need to trust the same certificate authority. And so when someone tries to send a message over, they can actually obtain the public key from the PKI. Since you trust the PKI, you trust the PKI to certify A, and you use the public key to actually do the digital signature that we've highlighted earlier. And then if it matches, you trust that this came from A. And so that's the idea of public key infrastructure. Okay, let's quickly move into the questions. So question 1, which type of cryptography uses the same key for both encryption and decryption? So we've covered this same key. It's always symmetric. This is same one key only. Asymmetric has 2 keys, private and public. So hashing, we've covered this is not encryption. This is separate. You cannot reverse. Encryption you can reverse. Digital signature, again, this is different. So for this, it's definitely C. Okay, question 2. Which cryptographic function is primarily used to verify data integrity? Okay, so when we look at data integrity, it's hashing over here. Okay. We haven't covered, encryption, so it's definitely not encryption. So key exchange would be, let's say we don't have a PKI, we have 2 separate people, and they want to somehow be able to communicate securely. They need to exchange a key among themselves. So key exchange is a way of, of setting up a common key between them without sending that common key. So that's key exchange. Yeah. Okay, question 3. Which algorithm is an example of asymmetric encryption? So, this is something that you just have to memorize, We've seen AES, DES is definitely symmetric. We haven't seen blowfish, so, if you haven't encountered it, it's a question mark. You just got to memorize the RSA, and the other one is elliptic curve cryptography, asymmetric encryption algorithms. Okay, question 4. What's the primary purpose of a digital signature? Compressed data? No. We are talking about security here, so it's not really compressed data. provide authentication and integrity, definitely. So this actually is also non-repudiation. It's provided also by a digital signature. So this is yes. Remember, the digital signature comes along with hashing, so there's no encryption involved, so this is wrong. Improved network latency, no, nothing related to that as well. Okay, question 5. Which cryptographic technique converts data into a fixed length output regardless of input size? Okay, this is something that we haven't really discussed earlier, but the answer to this would be hashing. So actually hashing, MD5 as well as, SHA. So there's multiple families of SHA. There's SHA-256, SHA-512, and this relates to the length of the output that it produces, and it's always a fixed length. If I'm not wrong, MD5 would be 32 characters when you convert it to ASCII. Yep. And I believe SHA-1, there's SHA-1 as well. SHA-1 would be 40 characters, I believe. Yeah. And it's always a fixed length. So for encryption and encoding, it can never be a fixed length, because mathematically speaking, the bigger the file, you need, after encrypting it, it needs to occupy, roughly equivalent kind of space. And so, when you decrypt it, you can get back the original. You can never ever encrypt a huge file into 32 characters and then, decrypt it back into a huge file again, because that would be, infinite kind of compression going on. So for encryption and encoding, since it's a two-way function, it can never be a fixed length output. So, mathematically speaking, this will be out. So, we are looking at hashing over here. Yeah. Okay, question 6. Which key is typically shared publicly in the asymmetric encryption? So the public key is the one that you share publicly. Kind of self-explanatory, private key is something that you keep private. So you just got to remember this. When we look at session key, so what happens is that, maybe a bit of an explanation, it may come up in the exams, I have no idea. So for HTTPS, something like that, it actually uses both, symmetric as well as asymmetric. And so the initial handshake, what happens is that they use asymmetric key to negotiate and and to generate something called session key. Because asymmetric, as we covered earlier, is very slow. So if you use asymmetric for every single packet that goes back and forth, it's just not good for performance. Yeah. So we use asymmetric to actually negotiate a session key, and then the session key is what is used what we use symmetric encryption for. So after that's done already, symmetric encryption is used for all the back and forth conversation that's going on. So that is the session key over here. So yeah, just in case it comes up, but for this question it would be a public key. Okay, question 7. What is the primary role of a certificate authority? Encrypt files, not really. The CA is not supposed to encrypt files for you. You are not supposed to actually send your files unencrypted anywhere else, because that's not really secure. You're supposed to encrypt it on the endpoint itself. Yeah. Issue and validate certificates. So definitely this is the role of the CA. So remember, earlier on we have a CA and we have all the different parties that need to trust each other, but they haven't met each other yet. And so what happens is that the CA would actually issue certificates to each person, and then they would validate. Again, if A sends a message to B, B can actually validate the digital signature with the CA. And so that's the purpose of a CA. No, you shouldn't really trust someone to store your passwords on your behalf. Maybe you may argue, the password manager does it. But the encryption should be done on the endpoint itself. Yeah, manage firewalls. Yeah, out again. Yeah. So for this question, it will be B. Okay, question 8. Which algorithm is commonly used for secure key exchange? So we haven't really covered key exchange in the preamble. We did talk about key exchange, just now when we talk about A and B. If there is no CA involved here, how do they communicate securely to each other, which is something called key exchange. So if you see something like this, you have no idea, it's process of elimination. So this is symmetric encryption. This is hashing. This is also hashing. So out, and so we have Diffie-Hellman as the algorithm that is used for secure key exchange. And so that's about it, and I hope that you learned something in this session, and thank you once again, and good luck for your exams.